Okay, let's go ahead and get started. Our question of the day was dogs versus cats, and I kind of knew it was going to go that way. Poor cats. The dogs are loved by lots of people. Let me just mention briefly where we're at, the plans. So you have hopefully finished homework 5. If not, you should be finishing that up first. And then you want to turn your attention to the midterm, which we've asked you to complete by Tuesday, and then have a 15-minute appointment with your TA to discuss the results of the midterm. If you do the test and have the meeting, you get the 10 points for the midterm task. I have posted a bonus that's associated with homework 4. It's only worth 2 points. I mean, this is more for people who are bored and interested in doing something a little beyond what we're doing in the normal assignments. This is following up on the inheritance ideas that I discussed in Wednesday's lecture. So it's kind of, it's not a lot of points. 2 points is not very much. So this is more for people who are interested in doing something extra. I expect that most of you will not do the bonus, which is perfectly fine. Okay, let me also just mention, we're not going to say a lot about the bonus or we don't even provide a lot of help for the bonus because it is intended just as kind of an extra thing for some people to work on if they're interested. So let me switch to the overhead, to the document camera. So let's switch over. Oh, no, actually, before I do that, sorry, I wanted to finish up this example that I was doing at the end of Wednesday's lecture. It was an inheritance example. I just wanted to kind of finish that quickly. So this is using the built-in AWT package in Java, the built-in graphics, early graphics. And we were overriding a frame class to have it do certain things. So it was kind of painting a little yellow square and printing some text. And I was trying to get this little code to work last time, and I didn't notice that I had typed an equal sign here instead of a minus. So that was kind of what that error was. So let me compile and come back over. So it's saying, by the way, it's giving little warnings here. It's basically saying you're using old-fashioned stuff. So are you sure you want to? It's a deprecated API. It's kind of not the official encouraged API. That's fine. We're using something that's the old-style stuff. What this one did is we had overridden a method called mouse down so that when I click the mouse, it draws a little blue dot wherever I'm clicking that mouse. They aren't really painted dots because, like, if I resize, remember how it shows you that it's repainting, the dots go away if you resize. I don't know if that's a bug or a feature, but we got our little blue dots. And I wanted to show you another thing with this, that I want to override another method that says that if I click on a spot and then I drag, so if I hold the mouse button down and I drag, I want it to kind of do a little etch-a-sketchy type drawing. I want it to follow the mouse as it does that and draw what it sees. So I'm going to come over here and I'm going to introduce another method, public Boolean mouse drag. So basically, when you understand how this frame class has been written, which I understand a fair amount about it, then you're able to override specific methods like the mouse down or the mouse drag and have it do something interesting. So I can get the graphics object again. How about if we set the color this time to be color.red? So what I want to do is to draw a line from where it was before to where it is now. So I kind of need some extra fields in here. I need private int old x and old y so that in the mouse down method I can remember old x is what x was here, old y is what it is here. And then in this method what I can do is I can draw a line from old x, old y to xy. So, and then this requires me to return a true. It's a Boolean valued method. So let me go ahead and compile and come back over here and run this version. It's not going to do quite what I said, the Etch-a-Sketch thing. If I click and then if I drag, it's drawing red lines, but it's relative to where I clicked. That was the issue here is I'm not resetting old X and old Y. I almost like this more than the other one that I described. But if I wanted to do what I described in terms of the Etch-a-Sketch type behavior, I have to update old X here to be what the X is. I have to update, scooch along as I drag the mouse. And then if I come over here and go ahead and run this version of it, now if I click and then drag, it's doing the Etch-a-Sketch type thing, where it's drawing a red curve, from where I'd been. Maybe we'll even do one other little thing here, which is I'll make a copy of this method, and because I'm going to do something that's a very similar method, and I'm going to do a similar thing, that what I'm going to do is when the mouse is up, I wanted mouse up. My fingers are not on the right spot on the keyboard. I want to draw a blue oval there. So if we kind of compile and run this version of it, this will be kind of the final version. So when I click, it draws the blue dot, and then the Etch-a-Sketchy type thing, and then when I let go, it draws another blue dot where I let go. So I don't know if you find that interesting or not. You can resize if you want. You can. I'll put this on the calendar for today, so you can download and play with this yourself if you want. I mean, the point was just that inheritance can be useful. That this is a case where they have created a frame class that has a whole lot of interesting behavior to it that's not actually visible until you override the methods and give them new definitions. So anyway, that was this final little inheritance example that I wanted to do with you. Let me switch back over to the document camera. Let me send that to the projector and be looking at the same thing that you're looking at. So what I want to talk about today is sorting. And I have a way of thinking of this that I think is a kind of a fun thing to do, although it's a little less fun when you guys aren't here to participate. But I like to imagine a challenge that, if I was doing a technical interview at a company like Google, and you were there, and I wanted to figure out, are you someone I would want to hire, that a task I might give you is I might say, I want you to spend the next hour writing a well-behaved sorting routine. So I'm giving you an hour to do it, and I don't want you to look up anything on the web. I don't want you to look up anything in books. I want you to just write code. You've got an hour to produce a well-behaved sorting routine. This is a fun thing to discuss with the class, because I'll get people in the class. One of the questions people will ask is, what do you mean by well-behaved? And my answer is, that's up to you. I mean, that's kind of one of the things that I'm interested in. Is what's your sense of what a well-behaved sorting routine would be? So kind of how do you interpret that? So I'll throw the question back. Sorting is something that the sorting algorithms are some of the most common algorithms that we end up discussing. We often are thinking about sorting things in an array. I wanted to mention a couple of sorting techniques that are not quite good sorting techniques, but they're interesting to know. Bubble sort is an interesting sorting technique that a lot of people know. So normally in the class, I'd ask people to raise their hand if they've been shown bubble sort. If they know what it is, they've seen it, and lots of people raise their hand. There are a lot of teachers who still teach bubble sort. I have a friend, Owen Astrachan, who teaches at Duke, and Owen hates bubble sort. He tried to get rid of it at one point in time by contacting a lot of people. Owen thinks that we should replace it with BOGO sort. BOGO sort would be, I usually talk about this. I'm going to do this in a minute. I'm going to actually work with some playing cards. But the kind of idea would be these things aren't in order, by rank. I want ace 2, 3, 4, etc. So, the BOGO sort way of doing this is you look and see they're not in order. So what do? I throw them up on the air, pick them up from, are they in order? No. Pick them up and see if they're in order. Are they in order? No. Pick them up, see if they're in order. BOGO is supposed to be short for bogus. If you were here, maybe some people would be chuckling or laughing or whatever. Owen likes BOGO sort because at least it gets a laugh. You'll find it actually, if you Google, you'll find that this is something that in the computer science community there really is a notion of BOGO sort, stupid kind of sort, where you just randomize and see if it's sorted. Well, Owen wanted to replace bubble with that, but he actually found there are a lot of people who like bubble sort. I think it's one of the least intuitive sorting algorithms ever. So let me kind of describe it with just array style operations. And then for the other sorting techniques I'm going to talk to you about, we'll use playing cards. But basically what you do is you take a look at these two elements, and if they're out of order, you switch them. Then you move over one position, and you look at the second and third, and if they're out of order, you switch them. Then you look at these two, and if they're out of order, you switch them. So you look at kind of, adjacent elements, and if they're out of order, you switch them. So you go through the whole array doing that. And then the question is, where does that leave you in the end? Well, the idea of the bubbling is that somewhere along the way, you're going to encounter the largest value. And big bubbles bubble to the surface, faster than small bubbles, I guess is the idea. Whenever you encounter that max, it's going to get swapped all the way up to the top. So that no matter what, with a bubble sort, you know that you're going to end up with the maximum value right there. That's the only thing you're guaranteed. In fact, if you have a list in reverse sorted order, that's the only thing it will accomplish, is to get the largest value to the end. And then the other numbers will still be in reverse sorted order. So bubble sort requires you to go through more than one pass. So you can do it again, but you don't have to go quite as far. You only have to bubble up to here. And then the second largest thing would go here. Then you bubble up to here. The third largest thing goes here, and so forth. So that's kind of the bubble sort. If I was kind of thinking of how many steps are involved, if I kind of put a dot for, well, I compare these two, so there's a dot to indicate that I compared to, a dot, for comparing to, potentially swapping. So if I kind of put a dot for each of the different things that I'm working with, I kind of end up with a certain number of dots. And then the next time I go through, and that gets me the maximum value at the end. The next time I go through to do this bubble sort, I'm not going to have to go as far. I can end one earlier than I did before. And when I do it again, I can go through and end one earlier than that. And then I can end one earlier than that. So bubble sort gets faster as it goes through because it's dealing with shorter and shorter lists. And if I did this all the way out, I think you'd kind of see that what I end up with is a triangle, a kind of an n by n triangle of dots. I'm not trying to give you a formal proof here. I'm trying to just kind of give you an intuition. Remember when we talked about complexity, that we said that you count how many times different lines of code are executed, and the line of code that's executed most often is the one that predicts the big O. So in the bubble sort case, it's the comparison, and how often, so there's like n minus 1 comparisons the first time, and then one less than that, one less than that, one less than that, gets faster and faster and faster. But, it's basically n squared over 2 dots here. So this is an O of n squared algorithm. We would say this is an n squared sorting algorithm. In terms of me doing this technical interview, one of the things that I would hope is that you would be familiar with the fact that a lot of standard sorting routines are n squared sorting routines, and that a well-behaved sorting routine, an n squared is not a well-behaved sorting routine. Works fine when there's a small number of things. But as n gets large, O of n squared is going to be too expensive. So I would want you to give me something better than an O of n squared sorting routine. So I would hope you wouldn't give me bubble sort. Maybe you'd make me laugh by giving me BOGO sort. But I'd hope you do something better. But I do want to talk about some other sorting techniques. So I've got some piles of cards here. So I took, oops, I dropped some cards on the floor. Let me grab that. Okay. I split up my 13 hearts into kind of 6 of one, 7 in the other pile. So I want to talk about 2 different techniques. So the idea would be, suppose I want to put these in order by their rank. So, ace is the lowest card, so it's supposed to be at the front. So suppose that I wanted to do that. one of the ways that I could do that is I could look through this pile of cards to find the smallest one. So 4 is the smallest one I've seen so far. 2 is even smaller, so I kind of remember the 2. And then I keep going, oh, an ace is even smaller than that. So the smallest card I've seen is the ace, and I would pull that out. So then I would go through it again, and I have a shorter pile than I had before. 4 is my current minimum, but then when I encounter the 2 is smaller than that, and nothing is smaller than the 2, so the 2 would be pulled out. And then I kind of scan through here. Which of these is the smallest? It's the 4. Which of these is the smallest? It's the 6. Which of these is the smallest? It's the 10. And then I'd do this one. So the way that I put it in order was by searching through the cards to find the smallest one and then putting that at the front. And that has kind of the same pattern that the bubble sort does, that I have to look at n different things to find the smallest one the first time through, but then it's a shorter list the next time through, shorter, shorter, shorter. So it has a similar kind of dot pattern. It's also an n-squared algorithm, what I was just showing you there, and that's known as selection sort. That's a famous sorting routine, and I think it's something that people, will tend to discover on their own. I think it's an intuitive sorting routine that you might do. So you go through the pile to select the minimum, and then go through what's left to select the minimum of that, and then go through what's left to select the minimum of that. So that's a way to sort with selection sort. But it has that same kind of dot pattern, where it's an O of n squared, because it does n dots initially, but then it gets faster and faster. All right. Well, let me mention to you what I think is probably the most common sorting technique that people tend to use, which is you say, okay, I've got a 3, and so now I'm going to look at my next card. There's a 7. Well, the 7 comes after the 3, so I'm going to keep it like that. Then I've got an 8, so let me put this where it belongs. So the 8 would go there. And I got a 9, it would go here. It's semi-sorted, but then I have the queen would go here. Where would the 5 go? Well, I'd kind of search through here, and I'd be looking for where to insert it. This is known as insertion sort, and then the king gets inserted at the end. So you build up a sorted pile slowly but surely by inserting at the appropriate spot, and this is known as insertion sort. Insertion sort. So now insertion sort was really fast at the beginning because there was only 1 card, and then there were 2 cards, and then there were 3 cards, and then there were 4 cards, etc. Eventually, you get down to, having to, when you do an insertion, if you have a huge list of things, inserting could require you to have to go a really long way to find out where the insertion goes. So, but, you end up with this sorting routine is one that goes quickly at the beginning but slows down as you have a bigger and bigger pile to insert into. And so it's kind of also an n by n, half of an n by n square of dots. It's also an n squared sorting routine. But it's a popular sorting routine. If n is not large, insertion sort is kind of probably the most common sort that people tend to use. So that's some of the standard sorts. None of those are ones that I want to use. I want to use something more efficient. And so I'm going to show you something that's known as merge sort. So let me mention the idea of merge sort. That basically you start with a list of things to sort, and you kind of break it up into half of them over here and half of them over here. You sort this half, and you sort this half, and then you merge it back together again to kind of come up with a sorted list. Well, I happen to have, used the hearts here. This is like half of them in sorted order. This is half of them in sorted order. So if I kind of think about what would it be like if I took half and did the sorting, how do I merge? Well, I just look at the top card. Which of these is smaller, the ace or the 3? It's the ace that's smaller, so I'd kind of use that next. Which of these 2 is smaller? It's the 2. Which of these 2 is smaller? It's the 3. How about these 2? It's the 4. Between these 2, it's the 5. Here it would be the 6. Here it would be the 7, 8, 9, and then the 10, and then the jack, and then nothing is left there, so I just bring these down. So that's kind of the merging operation. If you have two sorted piles, you can merge them into one. That's going to be the idea of how the merge sort is done. I did want to mention, so I mean, I mentioned that I would make this a challenge, for people to, you've got, say, an hour to create this well-behaved sorting routine. And I wouldn't want you to do an n squared. I mean, so I'm being maybe a little tricky that I wouldn't be very happy if that was your answer. I want something better than that. But in a way, I'm tricking you into thinking that if you wanted a sort that goes fast, that would be very quick, you might imagine that you'd want to program quick sort. Quick sort is a well-known sorting routine that runs faster than merge sort on average. So quick sort tends to be a faster sort than merge sort. And it's a very commonly used sort. It may be one of the most commonly used sorts that people use. In the Java class libraries, the built-in sorting routine is a merge sort. In .NET that Microsoft did, the built-in sort is a quick sort. I think the Microsoft people were more obsessed with it being fast, and the Java folks were interested in a different property that I'm going to explain to you at the end of the lecture. So between these two, I mean, I have an analogy for this that, I remember the days before we had all the social distancing and everything when we'd get together for Thanksgiving. And, a lot of my friends, we would have kind of different uncles who would come over for Thanksgiving. And you have kind of your, boring but very reliable uncle that comes over. Maybe that uncle, always remembers to send a check to you for Christmas and a check on your birthday. But they're kind of a dull person. But they show up early for Thanksgiving. They always bring a dish, like maybe one of those Jell-O things with marshmallows in it that looks really awful but tastes delicious. So you kind of know your reliable but somewhat boring uncle. Then there's your crazy uncle who rides a motorcycle. And so everyone's a little worried that, that someday he might wipe out. He doesn't send you checks on your birthday or Christmas. And he doesn't bring anything to Thanksgiving. Shows up late, and so you're all wondering, was there an accident or something? But somehow there's just kind of something flashy, and you like in some cases, the crazy uncle more than the reliable, the boring, reliable uncle. So the merge sort's the boring, reliable uncle. Quick sort's is the crazy uncle. We're going to do merge sort today. On Monday, I'm going to do quick sort as an optional lecture. So I've mentioned that I know that a lot of you will choose not to watch Monday's lecture, which is perfectly fine. But if you get interested, we're going to implement quick sort on Monday. I think that the thing is that I think it would trick you to kind of do quick sort because it's hard to do quick sort well. Just like the idea of someone riding a motorcycle. Quick sort, when it works well, is faster than merge sort. But when quick sort falls apart, it becomes like these n squared sorting routines. It becomes as bad as these other ones. So it's hard to write quick sort well. Merge sort is not so hard to write well. So let me give you an example with the merge sort, and then we're going to switch to looking at some code. So here's kind of what if you're sorting numbers. So you take your, this is a list 8 long, you'd split it into 2 lists that are 4 long, you'd split those into lists that are 2 long, you'd split those into lists that are 1 long. So splitting would be going on. Then you merge these two into a sorted list 2 long, you merge these two, merge these two, merge these two, and so that you end up with 4 lists that are 2 long. You merge them to have 2 lists that are 2 long. You merge that into this list. So let me do this list a little more slowly. I kind of would be helpful to have 3 fingers. One that would be here, one that would be here, and one that would be down here. But remember, what was I doing with my piles of cards? I was kind of looking at the top card here, the top card here. What's the next thing here, the next thing here? And between the -3 and the 18, which one is smaller? It's the -3. So I'd bring that down to here. And then I'd be positioned here. And which of these two is smaller? It's the 13, so that comes next. Which of these two is smaller? The 18, so that comes next. Which of these two is smaller? The 42. Which of these two is smaller? The 50. Which of these two is smaller? The 53. Which of these two is smaller is the 92. then you've used up everything from here, so anything left over here you just bring down and add it to the end. So basically what we're doing is that we are taking a list and we're kind of doing what I would describe as a split, split, split operation to come up with these shorter split operation. Split, I can spell. And then what we ended up doing was we kind of did a merge, merge, merge. Maybe I made that one a little too long. That was merging a little too much. But there's kind of a merging operation and then another merging operation and then another merging operation. And so, again, I'm just kind of trying to appeal to intuition. I'm not trying to prove things to you. But this splitting, going from here to here, kind of took n operations. There's n values to be split into these lists, and then another n values to get to the next level, another n values to get to the next level. So there's kind of n amount of work done here, n amount of work here, n amount of work done here, and then in kind of merging them back together, there's n things to merge here, n things to merge here, and n things to merge here. So that basically we can kind of think of this as that there are 3n steps to do that are splitting type steps. There are 3n steps to do that are merging type steps. So the question becomes, why 3? Where does 3 come from? Well, I started out with 8 things, and I divided it in half, divided it in half, divided it in half, divided it in half. This is a lot like what we discussed last time with the binary search. When you divide something in half, divide something in half, divide something in half, how many times does it take to get down to a list that would be of length 1? And the answer is log to the base 2 of n. 3, where that comes from is that's the log to the base 2 of 8. You have to divide 8 by 2 3 times to get it down to 1. So they're kind of, n log n operations that are splitting, n log n operations that are merging. It doesn't matter that there's kind of both of those things. The overall result is that this is n log n steps involved. You could say 2 times that because there's some here and there's some here, but we don't care about the times 2. And we don't care about the fact that it's to the base 2. All of the logs are the same, differed by constant. So this sorting routine, I'm just trying to explain to you the intuition why this is an n log n sorting routine. And we're comparing it to these n squared sorting routines. And so it's unfortunate that we have an n, but log n is a whole lot better thing to be multiplying by than an n. I had mentioned this idea that 2 to the 10th is around 10 cubed. So if you were, say, dealing with 10 to the 9th, which would be what? That's 1,000 million, a billion things, that would be around 2 to the 30th. So the one sorting routine would take a billion operations, and this sorting routine would take 30 billion. A whole lot better to have 30 billion than a billion. So that's why the n log n it's very important to have something that would go fast like that. That would be an n log n sorting routine. Boy, we're running short on time here, so I got to be careful. But let me mention one last little thing, which is quicksort, kind of the basic idea. Quicksort involves using a pivot value. And we'll talk about this in Monday's lecture, that it matters a lot what the pivot is. I happen to know that for cards that go ace through king, that pivoting about a value like 6 is more or less a pretty good pivoting thing. So I'm going to divide this into 2 piles, things that are greater than 6 and things that are less than or equal to 6. So these things are greater than 6. These things are less than or equal to 6. And so I kind of split into the 2 piles things that are less than or equal to 6 and things that are greater than 6. And then if I did some way of sorting within this little group over here, these are now in sorted order. These are now going to, well, we have 8 and then 9, and then I'll have the 10 and the jack here. The 7 goes up front, queen, king. So I put these into sorted order. So quicksort is similar to merge sort in that you split into 2 halves and then you sort each half. But because of the way that we split, we put things that were less than or equal to 6 over here and things that are 7 or greater here. These piles, all I have to do is just put them together. They're going to be in sorted order if I just put the one pile of cards underneath the other pile of cards. So there's no merging. There's no merge step involved. That's kind of the savings that a quick sort gets that allows it to run faster when that split works well. The split doesn't always work well, and that's why quick sort isn't always a good choice. Or at least it has to be written very carefully in order to kind of have confidence that it's going to work well. Well, let me switch over to the computer. So the idea is for us to try to write this sorting routine to get the job, and it would be good if I let you guys see that too. So we'll do send to projector, and then let's take a look so that we're looking at the same thing here. I have a program called Sorter. And so what I've decided to do in order to write a well-behaved is I didn't want to just use simple ints because that's a little too easy. So I decided I'd sort strings. I put strings in a sorted order. And in terms of the structure that I want to use, the merge sort doesn't require anything beyond queues. So I decided that I'd like to assume that I have queues. I'm sorting a queue of strings. That's kind of the task I'm solving. And I'm going to compare what we write against the built-in sorting routine. I'm going to time each of them and see how fast ours runs relative to theirs. And I don't know if you have kind of a sense of how fast you think it should be. They've had 30 years to get theirs to run fast, where we got 20 minutes to get ours to run fast. But let me try running it, and we'll see what it reports right now. Right now, the ratio is 0. We are infinitely faster than their sorting routine. Oh, but it does say the lists don't match. This program, I'll post this to the calendar today too. It is a program that checks and makes sure, so it'll kind of keep us honest. Why didn't it do anything? Well, that's because this is my sort. It's empty. So I haven't written anything yet. So that would be infinitely fast, but it's not really a sorting routine. So we've got to fix that up. I've copied here those values that I was showing you in the example with the overhead camera. Just to have some numbers, just to have that example available to be thinking about. So what I want to do first is I want to think about the merging operation. So I want to write a public static void method that I'm going to call merge into, that takes a queue of string that I'll call result, and I'm going to pass it also a queue of string that I'll call half1, and a queue of string that I'll call half2. So I'm going to have two queues, half1 and half2. Maybe I'll put this on the next line so that you can kind of see those parameters there a little more clearly. So 3 parameters, a result in half1 and half2. And let me go ahead and include some comments here that talk about what I want to have be true here. So I'll say that the precondition here is that result is empty, because that's where I'm going to store my answer, but initially it'll be empty. And list 1 and list 2 are in sorted order. So I'm given 2 sorted lists to merge into 1 sorted list. So that's like the 2 piles of cards that were in sorted order, and I'm turning it into 1 pile of cards in sorted order. So the post condition is that values from list 1 and list 2 are moved into result so as to preserve sorted order. So at the end, I want half1 and half2 to be empty, and I want everything to be in the result and in sorted order. So that's our goal, is how to do that. Well, how are we doing it when I had kind of those numbers there? You know, I had kind of a finger here. I was kind of checking out this value versus this value right here. And I was trying to figure out which of these 2 things was smaller. So what is it that I'm doing there? There's some kind of a test that I'm doing. And I'm comparing kind of the what's at the beginning of the one and what's at the beginning of the other. And you may remember that with my piles of cards, I was just kind of looking at the top card. Well, queues let you do that using the peek command. Remember that you're not allowed to use peek on your exam, but I'm going to use it here. So we kind of want to be able to have half1.peek, and we want to be able to do half2.peek. We want to peek at the top card, of each of the 2 piles. And so what do we want to do? Well, when this one is smaller, so like the -3 was smaller, so if half 1 dot peak is less than half 2 dot peak, then we want to move from list 1. I'm not half 1, sorry, I'm confused. Oh, yeah, I didn't want to use these names. I wanted to call them list 1 and list 2. I think I called them that in my comments. I do want to use those other names later, but I wanted to, let's call these list 1 and list 2. List 1 and list 2. So I've got my two different sorted lists. So move from list 1 to result, would be what I would do in that case, and otherwise move from list 2 to result. So that's what I was doing over and over again, is I was comparing kind of what's the current card in the one versus what's the current one in the other, and whichever one is smaller is the one that you take. So if the first one is smaller, then you move from it to the result. Otherwise, you remove from the second list to the result. Well, how do we move something from list 1 to the result? Where this is all, if you haven't done the midterm yet, this is all on the midterm. You have to remember how to do stack queue type stuff. So this is a little bit of queue review for you. That what we want to do to take it out of list 1, we would say list1.remove. And remember that that returns the value that it has removed. So we can say result.add what we get by doing list1.remove. So that's how we would move something from list 1 into the result. We do a similar thing here. We would add list2.remove. So there we take something from the second list and add it to our result. So that would be kind of our little if-else. If I compile, I get an error message that we need to think about. Bad operand types for binary operator less than. So it turns out that, let me go into the interactions pane. So you can ask for things like whether 3 is less than 4. And that works. But suppose I had, say, a string S1, which was Biden, and I had a string S2, which is Trump, and I asked whether S1 is less than S2. So that's what I'm trying to do here, right? The peek command would return to me the first thing in the queue, and it's a queue of strings. So that returns to me a string, this returns to me a string, and I'm asking whether the one string is less than the other string. Well, let's see what happens when I try to do it in the interactions pane. Operator less than cannot be applied to java.lang.string, java.lang.string. You're not allowed to use a less than comparison for two objects. So we've been doing things like less than, but we have to do something different when we're dealing with objects. And I mentioned that I'm doing strings because I wanted this to be a little more general purpose. So that's why, it would have been easier for us to deal with the ints, but this is something that we need to understand. Well, this is something that's discussed in chapter 10, and we're going to have a lecture where we talk about this more and a section where we practice this more. But there is a convention that in Java for how to compare one object to another object. So if I ask S1, the string class has a method called compareTo. So I can ask one string to compare itself to another string. So that's kind of the way that this is done, is that instead of using an operator like a less than, we call a method. So there's a compareTo method in the string class, and the convention is that it returns an int. Well, there's 3 possibilities for the comparison, right? If I ask you, how does this one string compare against the other? And this is alphabetical. Strings are compared alphabetically. So we would say that Biden alphabetically comes before Trump. So we would say it has a less than relationship. Well, so the convention is that if you ask string 1 to compare itself to string 2, if string 1 has a less than relationship to the other string, it returns a negative integer. If it has a greater than relationship, it returns a positive integer. And if they're equal, it returns 0. So let's take a look. When I ask S1, so Biden is alphabetically less than Trump, and it returns a negative integer to indicate that. If we had asked S2 to compare itself to S1, then S2, the Trump string, would say that it's alphabetically greater than Biden. So it returns a plus 18. And if we ask, say, S1 to compare itself to S1, those are strings that are equal, and it returns a 0 to indicate that they're equal. So as I said, we're going to talk about this more later, but we're seeing a little bit of it today. Let me make a copy of this if, so that I can remember what it looked like before. But the idea then is that you ask the one object to compare itself to the other object. And the convention, there's kind of a nice rule of thumb for all of this, that if you originally wanted to know whether there was a less than relationship, you see whether the compare to method returns something less than 0. If you wanted to see a greater than relationship, you see whether compare to returns something greater than 0. So basically, whatever relationship you were looking for, you put here relative to the 0 value. So that's how you kind of do the equivalent of comparing things, since we don't have the less than available to us. We ask the two strings to compare each other, and if the first one, when comparing itself to the second one, returns a negative, it means it's a less than relationship. But you remember, we did this for more than just one thing, so we don't want just an if here. What we're going to want to do here is we're going to have some kind of a loop. While something is true, we're going to want to do this multiple times. So let's scooch that over. And so what would be the test that we would want to use there? Well, we want to keep going as long as there's something in each of the two different lists. So we've seen this kind of thing before. We know that list 1 has an isEmpty method. We know that list 2 has an isEmpty method. We want to know that it's not the case that list 1 is empty, and it's not the case that list 2 is empty. So we want to make sure that they're both non-empty. So as long as there's something in each of them, we'll do the if-else. We'll do the peeking in order to decide how to get a value. Afterwards, we're going to have some things left over either in list 1 or in list 2. Suppose that there were things left over in list 1. How do you move everything from list 1 into result? Well, again, that's kind of code you're going to be writing on the midterm. While it's not the case that list 1 is empty, I would say result.add list1.remove. That's how I would, if there's extra things left over in list 1, that's how I'd move them into the result. If the extra things were left over in list 2, I could say, well, it's not the case that list 2 is empty. What I want to do is result.add list2.remove. So I'd kind of move things from the second list. You might think I need an if-else there. Is it the first one that has stuff or the second one that has stuff? But actually, the while loop test kind of serves that purpose for us. One of these two loops will do something and the other one won't, because one of them will have kind of some extra things left over. The other one will tend not to. So I think we finished the merge into code. Let me compile and make sure I haven't introduced, end the interactions. Let me make sure I haven't introduced a compiler error. It looks like I haven't. But we're running a little short on time. We want to try to finish a sorting routine. So we want to be quick. That means we don't want to write a whole lot of lines of code. What would be a way to do something fast? And the way to do something fast is with recursion, right? So what would be a simple list to sort? Empty list is easy to sort. One element list is easy to sort because basically there's nothing to do. So I could say if list.size is greater than 1, then there is something to do. Otherwise, there's a kind of an implied, else there's nothing to do at all. So our base case is going to be that we get to an empty list or a list that's 1 long. But if it's got 2 or more things in it, then I'm going to go ahead, and here's where I wanted to have something called half1, a new linked list, and then let me make a queue of string half2, which will be a new linked list. So what I want to do is I want to split the list into the 2 halves. How many things would go into the first half? Well, we know the size of the list, and we can divide by 2. How many things would go into the second list? You might think it's list.size over 2, but that doesn't necessarily work because what if there's an odd size? Then that doesn't quite work. We could throw in some use of a mod 2 or something. Some people know that a cute way to make this work is to take list.size minus size 1. That's kind of an easy way to guarantee that they add up to the overall size. So I can write a for loop for int I equals 0, I less than size 1, I plus plus. What I'm going to do is I'm going to move things from my original list into half1. So I'm going to do half1.add list.remove. So I kind of build up half1, size 1 times, for int I equals 0, I less than size 2, I plus plus. I can say half2.add what I get by doing list.remove. In fact, that second for loop could have just been a while loop, while list is not empty. So we would expect that when we get to here, I've moved everything from list into the 2 halves. List will be empty, and I'll have these 2 halves. So that kind of sounds like, couldn't I call merge into, passing it the list and half1 and half2? Couldn't I do that? Because list is empty now, and I've got my 2 halves. Well, but remember, list 1 and list 2 have to be in sorted order. Oh, and they're not necessarily in sorted order. They're queues of strings that I want to put into sorted order. A queue of string that I want to put into sorted order. If only I had a method that would put a queue of string into sorted order, I could call sort on half1, and I could call sort on half2 to put them into sorted order, and then I would satisfy the precondition for merge into, and then I'd be done. Then, well, other than having some kind of an error here, new link. I misspelled linked list. I have an I that's a capital I instead of a lowercase I. But once the compiler errors are done, let's go ahead and run it. And we took 2.4 times as long to run, so a little bit slower. But hey, we've only spent 15 minutes, and they've had, as I said, 30 years. The lists match, so that's good. We got an answer that matches, but it says it's not in stable order. So let me spend the last few minutes mentioning about this idea of being in stable order. So I'm going to show you a little spreadsheet here. So this is from our Assassin program, the names we were using. And suppose that, this is meant to be like a 1 means a freshman, a 2 means a sophomore, and so forth. So this is a list that's kind of jumbled, in general. I'm going to go ahead and say, I want you to sort by column A. So it's put them into alphabetical order. These things are in alphabetical order now. But now suppose I want to put them in order by their year in school. I want all the freshmen grouped at the top, all the 1s at the top, and then the 2s, and then the 3s, and then the 4s, and so forth. So there's a bunch of different ones, Alonzo Church, Grace Hopper, and so forth. And they're all tied if they are a 1. So they are equal keys. They could be in any order whatsoever, and we would say it did correctly sort because it did put all the 1s at the top. But take a look and see what happens when I sort by column B. It's got all the 1s at the top, but notice that they're in alphabetical order. It has preserved the order that it had before. That's what's known as a stable sort. I'm going to give you a little example program that does something for that. When I run this program, this is a program that has a bunch of different words, from the 7 years ago. And it puts them into sorted order alphabetically, A followed by a go, all, etc. So these things are in sorted order alphabetically. And then I do a custom sort where I put them in order by length, so that I have all of the words of length 1, followed by words of length 2, followed by words of length 3. Take a look at these words of length 3. Do you notice anything about them? They're all in alphabetical order. It preserved the alphabetical order that I had set up with the first sorting routine, just like what I just showed you in the Google Doc. So a stable sort is one that preserves the relative order of things that are tied, keys that are equal to each other is the way we would describe it. Quicksort, it turns out, is not a stable sort. Merge sort can be a stable sort, but I kind of blew it on purpose when I wrote the code with you, which is that when we were doing the merging, I said that if the first one is strictly less than the second one. So what happens when they're equal? I was drawing from the second pile when I want to draw from the first pile. So to make my sort stable, I need to use a less than or equal to. And then when I run it, it's going to compare them and show me how they compared. And it shows me that they match and that it's stable. Okay, Monday's optional lecture. You should be working on your midterm. You could skip the Monday lecture if you want to do the midterm instead. I'll see you by Wednesday of next week when we'll be looking at new material.